The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, my name is Suha Soilu and I'm the Director of Operations at Hosokawa Micron Powder Systems. We at Hosokawa Micron Powder Systems and K-Tron International welcome you and thank you for attending our next in the series of educational webinars entitled Innovations in Continuous Processing. Let me point out, if you have any questions during this presentation, you may submit your questions online at any time. Please refer to the Q&A pane on the right side of your screen. At the conclusion of the webinar, we will try to accommodate all of your questions during our question and answer forum. Hosokawa Micron Powder Systems is a division of Hosokawa Micron Group with headquarters in Osaka, Japan. We are the global leader in powder processing equipment with over 1,500 employees worldwide, production facilities in 5 countries, and 12 research facilities and state-of-the-art test centers. Hosokawa Micron Powder Systems, founded in 1923 under the name of Pulverizing Machinery, is responsible for the North American market. We, from our Summit, New Jersey office, provide sales, engineering, manufacturing, and aftermarket services for the food, pharmaceutical, chemical, and minerals industries. We are proud to be the inventors of the micropulverizer hammer and screen mill, as well as the most versatile and widely copied air classifying mill, the Micro ACM. Our brand names include Micro, Alpine, Riconauta, Majak, Micron, Stott, and Vital Air. I would like to introduce my co-host, Sharon Novak, who serves as the Global Business Development Manager for the food and pharmaceutical industries for the K-Tron Process Group.
Thank you, Suha. Hello, everyone. As Suha said, my name is Sharon, and I am the Business Development Manager. First, let me say thank you to Hosokawa for inviting K-Tron to participate in this webinar, and hello to the many customers from K-Tron who I see are also listening. For those of you who don't know K-Tron, K-Tron International is a global company based in Pitman, New Jersey. The K-Tron Process Group, a division of K-Tron International, is comprised of 3 separate divisions, including the following: K-Tron Feeders, manufacturer of all the feeding equipment I'll discuss today; K-Tron Premier Pneumatics, which manufactures pneumatic conveying equipment and specializes in overall system design; and K-Tron Electronics, manufacturer of the technical controls for K-Tron equipment. K-Tron's global network consists of several manufacturing and design locations, including those in Salina, Kansas, Pitman, New Jersey, Netherlands, Switzerland, and its newest acquisition in Wuxi, China. In addition, K-Tron includes several direct global sales offices, including those in France, Germany, Great Britain, and Singapore. K-Tron is represented by an extensive global manufacturing network, including more than 80 representatives in over 62 countries worldwide. The varied divisions of the K-Tron Process Group are responsible for several types of equipment suitable for the pharmaceutical industry. This equipment includes the specialized K-Tron feeders and highly accurate patented weighing systems, which we will discuss in detail here today. In addition to the feeder line, K-Tron manufactures the pneumatic conveying equipment suitable for the consistent refill of these continuous systems. K-Tron's in-house systems engineering group is able to provide completely integrated systems and controls for a wide variety of pharmaceutical operations. And now Suha will begin the technical content of this seminar.
I would like to start our discussion with the review of a basic tableting operation. There are 2 distinct approaches to this process, which are wet and dry granulation leading up to tableting. Although we will only review the dry process, the concept developed is equally applicable to both. As can be seen from the components associated with the dry process, this is a batch operation, in large part due to the blending steps where bin and V blenders seem to be the norm. If we were to quickly trace the process, the first step would be to blend the primary ingredients, excipient and the API, which is a batch operation. After this, the blend goes through compaction and dry granulation stage, typically to minimize the fines and improve the flowability characteristics. at which point lubricant will be introduced, again a batch operation, leading up to the tablet process. And here on this slide you can see the greens are identified as the continuous, and the reds are the batch processes, breaking up the overall process into basically making it a batch operation. Now that we've outlined the basic flow, we can look at the challenges associated with the batch nature of process. We will look at first at the material handling aspect. When there are multiple starts and stops, and with connecting and disconnecting devices, the chances of product contamination increases significantly. Alternatively, for potent mixtures, there is an additional concern of exposing the operators to the product. Switching over to a continuous process will eliminate all the make or break points associated with material transfer and sampling, hence isolating the process from its surroundings. The next major concern is the size of the equipment. Depending on the batch sizes, the vessels that need to contain these amounts get larger, creating logistical issues as well as cleaning problems. Again, with continuous process, the equipment size does not need to change in order to handle larger capacities. All that is required is to run the existing system for a longer period of time. As with any validated process, when moving from a development to pilot or production scale equipment, there will always be concerns with scale-up issues. When the physical size of equipment change to handle larger scale production, there are always concerns in making sure that the same end product can be achieved with the calculated scale-up parameters. As we discussed with the capacity issue, sticking with the same equipment and running it for extended periods eliminates the scale-up issues as well. Process control is another problem point with offline analysis, including sampling inconsistencies and delays in getting the results of the analysis back. Once again, with an inline analysis, the process control is real-time, and with proper control measures, any product that could be out of spec can be diverted to a separate location, preventing the contamination of good product. Continuous mixing technology has been developed to overcome some of the shortcomings of the batch mixing steps. There are several different technologies that have been introduced to provide a continuous blending operation, but they all go about it in a slightly different manner. As with any technology, each has their advantages depending on the application. The number of ingredients, the proportions, and the material properties will play a great role in making the decision with regards to the suitability of each technology. Although there are empirical methods for estimating the performance of these units, testing still probably is the best means of determining the right equipment selection. What are some of the key elements in determining the best equipment for your application? Certainly, with pharmaceutical applications, cleaning needs to be considered. Additionally, the responsiveness of the system is another key factor. If inline analysis indicates a deviation, how quickly will your system respond to correcting itself? What is the residence time of the material in the system, and what is the significance of residence time? What are the expected startup and shutdown losses? How flexible is the process? These are some of the questions that need to be asked as we delve into this technology. To get a better understanding of this process, we can look at a basic example where one excipient is being mixed with an API. With an overall required feed rate of 20 kilograms an hour, the API fraction feed rate is 400 grams an hour, which is about 2% of the total. The remaining balance of 19.6 kilograms an hour is, in this case, is the excipient. To exaggerate the effect of the variations in the feed rate, which is one of the crucial issues with continuous mixing, we have used a volumetric feeder for the API fraction, which is typically the very low feed rate ingredient. Here you can see with the dark blue line the variations in the feed rate from the set point of 400 grams an hour over time. You can see the blue lines with very large variations in the feed rate. The magenta line, on the other hand, is the concentration of the API at the outlet of the mixer, where it can be seen that the mixer is smoothing out the large variations that are in the feed to provide for a much more homogeneous blend. To understand this phenomenon and also be able to model our continuous mixer, which will further allow us to predict the performance of the equipment, we will look at a tracer pulse experiment. As can be found in the general textbooks on reactor engineering, the response of a pulse-wise added dye in the entrance of a plug flow, including axial dispersion, will result in the following type of concentration profile at the outlet of the reactor. In here you can see clearly this is a pulse, a signal that's being sent, and this is at the outlet how the distribution has changed. The formula shown in this slide is a mathematical approximation for the dispersion model that has been developed for tubular reactor flow. Here the two important parameters are the Peclet number, which is a dimensionless parameter derived from the axial dispersion coefficient. The lower the value of this number, the better the mixing that will take place. Hence, a Peclet number of 0 would indicate perfect dispersion. The second critical parameter in this equation is the residence time. In this slide, you can see the setup for the tracer pulse experiment, where an opening at the feeder downspout leading to the mixer is the location for the introduction of the dye. Here you can see the feeder, the downspout, and this is the mixer down below. And here you can see kind of black hole where the dye is actually, or the pulse is introduced. A belt conveyor has been placed on the discharge of the mixer to capture and evaluate the material. This gave us the capability of evaluating the output of the mixer over a given period of time. You can see the belt conveyor here and the material that's collected on it, which gave us the capability of looking at it so that we could do a time graph of this. Here, a typical cantilevered rotor is shown, where we will discuss further the adjustment of the paddle positions and the effect that they have on the performance of these mixers. Each vendor's designs, although being slightly different, provides for a somewhat universal control mechanism for the dispersion of the mixer. The analysis was conducted with our own visible light reflectance mixing sensor, which is shown on the right-hand photo. The photo on the left, on the other hand, shows the location of sampling conducted along the belt length to determine the concentration of the pulse dye, in this case a spoonful of red toner. In here you can clearly see where the samples were read off. We do have a 5-minute video of this experiment that can be made available to interested parties after the conclusion of this presentation. This graph shows the dye concentration on the discharge conveyor belt over time for several different paddle settings of the rotor. Curves can be fitted utilizing our dispersion formula. As can be seen from the dotted line curve, the theory coincides with the actual data fairly closely. This will allow us to predict the performance of our mixer, hence make the required adjustments to achieve the best possible performance for a given set of input conditions. In here you can clearly see the pink line, which shows the all forward paddle positions, while the orange one shows all backwards, and the yellow one showing a mixed paddle positions, which is correlating very well with the empirical formula. This is the same graph we saw earlier with the addition of the yellow curve, which is the theoretically calculated outlet profile. It is clear that the calculations closely mimic the actual data, which is the magenta curve here, with the exception of a slight shift in phase. This bar chart is another representation of the effects of the paddle positions to the Peclet number, the light blue bars, and the residence time, the purple bars. To achieve the optimal performance, a mixture of the paddle positions are utilized. The optimal paddle position, while getting the best performance from the mixer, also needs to address operational concerns like moving the material away from the feed end shaft seals and directing the mixture to the outlet. Keeping the residue to a minimum in the mixer is another major concern that is tied to the paddle design. I would like to introduce a new term, RSD, which stands for Relative Standard Deviation. This term, which is expressed as a percentage, is a measure for random error. My co-host Sharon will talk more in depth about this term later in this presentation, since this is a term most often utilized in describing the expected performance of the feeders. In the previous bar chart, we looked at the effect of the panel positions on the PEC lane number and the residence time. Here we take it one step further and look at the effect of the residence time on RSD reduction and the startup time. What can be seen from the dark blue curve is that the RSD reduction increases with an increase in residence time. This essentially means that the input variations inherent in feeders can be offset with an appropriate rotor setting. On the other hand, the downside to the increased residence time is the increase in the startup losses, which can also be seen from the magenta curve. Just to clarify further, there are unavoidable variations in the feeder output, which increases with reduced feed rates. Our goal is to smooth out these variations by dispersing the ingredients effectively. This effect is what we're graphing as RSD reduction, which will essentially guarantee the required dosage of the API making into each tablet. The other half of the performance data can be seen here, where the effect of the PEC lane number, which is the measure of dispersion, on the RSD reduction and startup losses. This time, the dark blue line shows that there is a sharp drop in the RSD reduction with the increase in the PEC lane number, meaning poor dispersion. Yet there's a significant reduction in the startup time, hence losses are minimized, which certainly is desirable. Ultimately, the target is to find the optimal spot where we can achieve the best performance with minimal losses. As I mentioned earlier in this presentation, there are several different continuous mixers available. The modular mix is one such mixer which combines an annular mixing profile and a modular concept. The theory is certainly not new. It is based on an existing batch mixer, the Cyclomix, which has been around for the last decade and used successfully in many different processes. The concept that has differentiated the Cyclomix from other conical mixers has been the ability to reduce mixing time significantly while maintaining high mixing accuracies. Taking its cue from the success of this concept, the batch mixer was converted to continuous, which has given birth to the modular mix. This unit has a unique annular mixing profile where the material stays between the rotor and the housing. This minimizes the amount of material in the chamber at any given time, hence making this unit very responsive. The rotor speed is variable, allowing for high-intensity mixing at 20 meters per second tip speed, as well as gentle mixing around 2 meters per second. With this unit, very accurate mixings can be achieved in very short periods of time. Also, the compact size of the units make them extremely suitable for cleaning and hence the pharmaceutical industry. These units can be stacked in series to allow for extended residence time if required, but more importantly, it will allow for 2 or more separate mixing intensities. With a typical API excipient blend, which requires high energy mixing, while the lubricant requires low intensity and gentle handling, this unit can accomplish both tasks with ease. The inlets that are placed on both ends of the unit are tangential to allow for main ingredient to enter the first unit, while the inlet on the tail of the chamber is used to feed the lubricant into the second chamber. Here you can see the excipient and the API would be brought in from this primary inlet port, and the lubricant could be introduced on the secondary inlet port, which you could see will directly feed it to the second mixer down below, which has a lower rotor speed for less intense mixing. This compact size unit can handle rates from 20 kilograms an hour up to 150 kilograms an hour, which would cover feeding almost any tableting operation. In this slide, we can see a slightly different design where the feed forms a bed within the chamber, almost like a screw conveyor. Since this is a single chamber unit, it employs a tilting mechanism to allow for additional control over residence time of the product in the mixing zone. This unit is similar to the others with adjustable speed rotor, but lacks the flexibility of varying intensities in a single train. The mixer shown on this slide utilizes an outlet weir to control residence time. Again, similar to the unit in the previous slide, the material bed is formed within the chamber, and by changing the angle of this outlet weir, the retention time of the mixture can be increased, allowing for possibly longer residence time. This unit, just like the other two, will also allow for the rotor speed to be adjusted for additional control of mixing intensity and dispersion. Finally, coming back to our process by replacing the V and bin blenders with continuous mixers, and you remember the V blenders were in these areas and we replaced them with our continuous mixers, we will turn this process into a continuous operation. As mentioned throughout this presentation, larger volumes can be processed with compact equipment, eliminating the revalidation associated with scaling, as well as establishing much more accurate process control with inline analysis techniques like NIR spectroscopy. This concludes my portion of the presentation. I hope you found the information today informative, and I thank you for your attention. With that, I will now turn it over to my co-host from Catron Process Group, Ms. Sharon Novak.
Thank you, Suha. This portion of the seminar will focus on the role of gravimetric feeders for continuous processes, as well as educate the attendee on the necessary information required for the proper design and overall integration. In the continuous process, the feeder chosen can not only affect the overall throughput of the process, but also the process end quality. In order to properly choose the right technology, it is critical to evaluate the material characteristics which affect the flowability of the material, the measured accuracy of the feed technology chosen, as well as the operational requirements of the feeder, such as cleanability, ease of maintenance, containment options, overall size, and controls and data acquisition. In continuous processing, the end process is often referred to as being a slave or a slave to the feeder or feeders. Feeding devices are used to set the overall throughput and flow rates of the process downstream. In some cases, a pre-blend of the excipients and API are introduced continuously in one feeder, with the lubricant usually introduced towards the end of the mixing stream, as shown in one of Suha's slides. However, in ideal continuous processes, each ingredient in the formulation is introduced by a separate feeder, based upon the percentage of each component in the mix. Due to this configuration, the overall accuracy of the formulation is highly dependent upon the accuracy of the feeder's delivery. In order to properly select the type of feeder which will accurately deliver the ingredient to the process, several key material characteristics should be evaluated. The characteristics listed on this slide will help the feeder manufacturer determine the overall flowability of the powder and thus indicate which feed technology is best suited. For example, bulk density will not only help to determine the proper volumetric flow of the powder, but also the volume of the refill hopper required to ensure constant flow. Particle size and morphology is also critical to overall flowability. A very free-flowing material is typically spherical in shape. Most APIs, however, are actually needle-shaped or include what is known as a high aspect ratio, the ratio of particle length to width. These needle-shaped particles tend to build up on one another instead of flowing easily over one another, like that of a spherical particle. This contributes to poor flowability. One of the easiest ways to assess an API is to simply look at it under a microscope. Chances are it's needle in shape and poor flowing. Moisture, angle of surface friction, compressibility, these are all characteristics which contribute to flowability aspects. Angular repose, as shown on the picture on the bottom right, is a critical measure which not only indicates flowability, but also helps the feeder or equipment manufacturer to design proper hopper angles. The properties of all the characteristics listed here aid in the classifications of materials into one of four categories: floodable, free-flowing, difficult to flow, and cohesive or sticky. In addition to cohesive properties, it's also crucial to determine if the product is too free-flowing, or what is called floodable. In this case, if the process downstream is under a negative pressure, for example, the floodable material can actually bypass the feeding mechanism, thus defeating the purpose of the feeder in the first place. This is actually very prevalent when you're dealing with volumetric feeders, as what Suha was talking about previously in his slide. And I'll talk a little bit more about volumetric versus gravimetric in a second. To fully define feeder accuracy, it is necessary to address three separate and distinct areas of feeder performance: repeatability, linearity, and stability. Repeatability reports how consistent the feeder's discharge rate is at a given operating point, while linearity assesses how accurately the feeder discharges at the requested average rate over its full operating range, and stability gauges performance drift over time. You can see the three graphs shown here will actually show you the three different types of measurements that are taken, and the actual rates are based upon the overall rate and distribution ranges of the feeder that you use. Repeatability is a performance statistic most familiar to feeder users. It quantifies the short-term level of consistency of discharge rate, and this is where it ties into the relative standard deviation that Suha discussed earlier. The repeatability measurement is made by taking a series of carefully timed consecutive catch samples from the discharge stream of the feeder, weighing them, and then calculating the plus or minus standard deviation of the sample weights expressed as a percentage of the mean volume of the samples taken. Suha previously explained standard deviation as a deviation from the average. Traditionally, repeatability has been expressed at 2 standard deviation, or known as 2 sigma, over a set amount of time intervals. Due to the increasing demands of downstream processing and the end quality standards that apply, manufacturers are now specifying repeatability up to 6 sigma for sampling periods as low as 15, 5, or even second-to-second time frames. The graph on the top right illustrates a typical standard deviation curve, 1 sigma at 66.3% of the sample, with 3 sigma up to here at 99.7% of the sample. Typically, the repeatability standards that can be expected from a gravimetric feeder are 0.25 to 0.5% of the set point, whereas with the volumetric feeder, as you saw in the graph that Suha showed, the variations can go anywhere from 1 to 6%. The graph on the bottom will actually show you a typical output graph of a feeder as a result and the function of weight versus time. This shown over an extended period of time but taken in 5-second intervals. Factors affecting accuracy include feeder selection and sizing, weighing resolution, control responsiveness, and environmental dynamics such as vibration and shock. The most common types of feeders used for pharmaceutical continuous processes are screw feeders. Screw feeders, as shown in the picture to the right, are available in both volumetric and gravimetric configurations and are typically available in both twin and single screw designs. The diameter of the feed screw, and this actually shows a twin screw design, here the screws being 2 here. The diameter of each of the feed screws can affect the overall delivery. For example, at a given rate, a smaller diameter feed screw will rotate faster than a larger diameter one. Single or twin screw feeders represent the most versatile feed technology for bulk solids. Given the material characteristics, a suitable screw configuration is made for the required rate. Single screw feeders, shown in the top photo, are often used for higher volume applications. They are also ideal for free-flowing materials which are not cohesive. However, typical problems which are encountered with a single screw include the material being flung off the screw flights here and onto the screw tube and sticking to the screw tube wall, which causes the material to then build up on the wall and fall off into clumps. This defeats the purpose of having a metered screw or metered feed delivery in the first place. For this reason, twin screws, as shown in the bottom photo, are often used for most cohesive powders. The twin screws are co-rotating, and they actually have a self-wiping effect, so that the material can be conveyed along the screw tube, and it prevents the typical problems of buildup encountered with single screw designs. By employing 2 self-wiping closed flight screws intermeshed side by side, sealed pockets are formed to capture and transport both hard-to-flow materials and also the floodable materials that we talked about before. Single and twin screw configurations are typically available in a variety of designs which differ in screw pitch and flight. As shown in the chart here, this is just an example of some of the different configurations that are available, changing both the pitch and the amount of configurations or screw flights in the screw itself. The difference in the screw configuration will not only affect how the material flows in the feeder, but will also affect how much material is delivered per screw revolution to the process below. So it's important to choose the proper screw configuration for the material that you're using. This graph, as provided by the ERC on continuous processing and actual continuous feeding trials at Rutgers University, illustrates several different screw configurations on a twin screw feeder for Avicel. Screw configurations were all tested both with and without a screen at the screw feeder discharge. The use of a screen serves not only to help disperse the material after it exits the screw feeder, but it also helps to produce a back pressure on the feeder, thus helping with overall screw fill and consistency. As shown in the graph, the feeder performance and accuracy can be affected based upon the screw configuration used, but also in relation to the overall screw speed that is utilized. So this shows the relative standard deviation of the feed rate, and this shows the percentage of screw feed that's used in the total range of the screw feeder used. These give the different configurations of screens versus type of screws used. And you can see the variations differ significantly depending upon the type of configuration you use. This just shows you how important it is that the proper configuration on the screw be actually utilized in order to make sure that you're making the most efficient means of conveying the material. When comparing different materials with varied cohesivity, as this is shown, where we are actually conveying or actually feeding Avicel and fast lactose as well as cellulose, you can see the differences between utilizing the different screw configurations also on the RSD. This illustration shows that screw configuration is very important to minimize those deviations from set point. More cohesive powders, for example, just because of their difficulties in flow, will have higher RSDs. Therefore, it is important that the proper screw configuration be shown to minimize this amount. By definition, a gravimetric feeder consists of a hopper and a feeder that is isolated from the process so the entire system can be continuously weighed. These pictures actually show several different configurations for gravimetric feeders, all on load cells or scales, here, or in this case, the whole feeder being suspended from load cells. As the feeder discharges material, the system weight declines. The speed of the metering device is controlled to result in a per unit time loss of system weight equal to the desired feed rate. Volumetric feeders, however, operate by delivering a certain volume of material per unit time. In the case of a volumetric feeder, the bulk material is discharged in the hopper by regulating the speed of the feeding device. The actual volume of the material fed is dependent upon the uniformity of the material flow characteristics and the bulk density. Most important, volumetric feeders do not control mass flow, which is critical for continuous processes. And these are one of the main reasons that you saw the variations in feed rate with the volumetric feeder on Suha's graph. The most popular type of gravimetric feeder used is the loss and weight feeder. As shown by the figure on the left, with volumetric feeders, flow rate changes are accomplished by altering feeder speed. In the case of a screw feeder, three factors affect the volumetric screw feeder accuracy: the consistency of the delivered volume per screw revolution, the accuracy of the screw speed control, and the material density variability. Typically, volumetric feeders are open-loop devices that cannot detect or adjust to variations in the material's density. With the volumetric device, the feeder is simply turning at the speed that was designated at startup. If the material is built up or bridging in the hopper, the feeder will not know it, and it will just continue to perform as if it was started up at the same speed that you told it to, which actually means that at some point during the continuous process, you may have a point that you're not feeding any material to the process itself or feeding little or no material. With a gravimetric feeder, as the feeder is losing weight, the weight is measured by the load cells or scale, and then a signal is sent to the controller, as you see here, to adjust the screw speed and maintain the constant mass flow. In the case of varying head loads, when you have different bulk densities that are changing as the hopper is declining in weight, the load cells will actually detect the change and adjust the speed accordingly. In addition, with the loss in weight device, the fact that there is no flow occurring also means that there is no corresponding loss in weight on the load cells, and an alarm will sound. In the case of some even more sophisticated feeder types, this signal can then be set to a vibrator located on the outside of the hopper, which will then vibrate in order to cause the material to unbridge and flow again. Once the mass flow is back in line with the set point, the vibration can then be stopped. Because the gravimetric device is measuring actual mass flow, it is referred to as a direct measuring device. The most important requirement for continuous feeding relies on the ability to provide real-time measurement of the flow of product to the process below. As discussed previously in Suha's slide, the use of a volumetric feeder will cause a wide variation in performance. As you can see here, 1 to 5 or 6% of the set point, depending upon the material. Due to the ability to provide more consistent feed rate, the gravimetric device will produce a much more accurate delivery and will also serve to even out the performance of the mixer. This slide illustrates how the loss in weight principle operates. In the plot of weight versus time, the feed rate set point is represented as a downward sloping line. The negative mathematical slope indicates the desired loss of system weight per unit time. The feeding cycle begins with a fully loaded hopper at the top, where the weight is set as a maximum. As the feeding proceeds, the measured weight is continually compared against the set point line's target weight. Any difference between the two values, as it declines in weight, will trigger a change in the feeder speed from the controller. For example, if an overfeed condition occurs due to an abrupt increase in material density, the sensed weight falls below the desired set point weight, triggering a reduction in the screw speed to return to the set point value. The opposite occurs in an underfeed condition. Now, what happens when the feeder is at its lowest point, as it is here, for a refill? When the hopper reaches a predetermined minimum weight level, the hopper is automatically refilled. This portion of the feed cycle in the continuous process is critical in order to ensure overall flow consistency because the feeder is operating volumetrically. But how does the feeder know what speeds to operate at to maintain consistent product output as it's filling back up? The answer to consistent flow is in trending and collection of the data which is occurring during the feeder loss in weight. This is also known as feeder refill array. The refill array technique automatically adjusts the screw speed during the refill as the weight is increasing. During the refill cycle, the controller regulates the speed of the feeding device based upon the historic weight and speed information that was collected during the previous weight loss cycle. This data is also referred to as a series of feed factors as shown in the graph. See the feed factors on the side here. So as the feeder is declining in weight, these feed factors are actually being recorded so that at the same point that the feeder is being refilled again, the feed factors are going back into place, and that is adjusting the speed so that we're maintaining the same mass flow. The refill concept is especially important and most accurate when using a high-resolution, fast-responding weighing system. By maintaining the correlating screw speed, a consistent and constant delivery of the ingredient to the process can be achieved. The accuracy and performance of the refill array is critical to this overall accuracy. However, even though the feeder is being trended with data to deliver the material to the process below, the feeder is still operating volumetrically. For this reason, it's critical that the overall amount of time which the feeder is in refill during the complete operation of the process be as short as possible in order to maximize the feeder performance. It is also imperative that whatever device is chosen for the refill, that the delivery of the product during the refill process be as quick as possible. This slide shows several different choices as far as refill options on the type of refill device that can be utilized above the feeder hopper. Options include knife gates, modulating butterfly valves, rotary valves, or in the case where extreme control is required, such as in microfeeding of very low rates, the use of alternate meter devices such as volumetric screw feeders. Pneumatic receivers, such as the device refilling the feeder in the photo here, operate under a dilute or a dense phase vacuum transfer principle, and are often used as refill devices. The pneumatic system utilizes negative pressure to suck the material required into the receiver, and then the receiver is filled to a determined level and then holds this material and is closed, isolated here by means of a butterfly valve, before the feeder below asks for a refill. When the feeder below asks for a refill, the butterfly valve opens, the material falls into the hopper here, then the butterfly valve closes, and then the feeder is again, the receiver is again charged for the next cycle. One of the things to show on this slide here that's also critical in any type of refill device that you use with a loss and weight feeder are the use of bellows or flexible connectors between the feeder as well as the process below, mainly so that the scale can always accurately define exactly the load that's in the feeder itself and send the signal back to the motor and the controller. When determining the best refill device for a continuous process, it is imperative that the flow rate from the refill device be sufficient to avoid exceeding the refill time limit. Additionally, the flow cutoff action of the selected device must be quick and sure. A slow tapering off of the refill flow lengthens the refill time, which will affect the amount of time that you're in volumetric, which will also affect the overall accuracy of the system. And then also any leakage of the refill device, such as sometimes with rotary valves, will actually cause an unavoidable measurable weight disturbance. In addition, it is important to evaluate the overall space and height limitations, which may exist for the refill device. For example, although gravity flow may be best from a segregation concern, there may not be enough height or space to deliver a variety of materials via several IBC bins to the feeder hopper. In this case, the use of a dense phase conveyor, which convey the powder from bins on the floor to the receivers above, may be better suited. In summary, all continuous processes require a variety of key design parameters which must be considered to ensure the consistent flow of the material to the continuous process below. Material characteristics are critical to overall feeder selection as well as resultant feeder accuracy. The use of single versus twin screw feeders or different screw configurations, as you can see from the previous slides, can greatly affect the feeder output. In addition, the design and choice of the proper refill device and the control system with a high accuracy and quick response refill array is critical to the overall performance. It is imperative that the design of the overall system not compromise the performance of the feeder, and that issues such as containment, isolation, and cleanability be thoroughly examined.
Thank you, Sharon and Suha. At this point, we're going to begin our question and answer session. The first question, how does load cell scale type affect accuracy in LIW feeding?
Okay, I'm going to take this one. LIW refers to loss in weight, for those of you that didn't pick it up in the slides before. With typical scale or load cell technologies, a lot of them are available in what's called an analog configuration. Analog weight sensors, like a strain gauge, for example, the output of the signal is low and it's susceptible to electrical noise, and so that distorts the measurement. For this reason, they often depend on the post-measurement amplification and digitization so that the error of the measurement will also exist. Typical resolutions of these devices are 1 in 100,000. The alternate design is the digital approach, which is actually what Catron uses with their own patented vibrating wire SFT load cell technology. This is a much higher resolution load cell. It's actually 1 in 4 million, and it's specifically sized and designed for the weights of the feeders and the material within the feeders so that the continuous weighing can be done specific for continuous processing. The SFT actually measures the frequency of the wire vibrations during the time measurement without amplification. In addition, the SFT also includes digital filtering algorithms, which allow the weighing system to be able to discriminate between the load that's being measured and the forces that are imposed by, say, plant vibration. So that's critical to the operation of the load cell itself.
Okay, next question from the same viewer. How does LIW feeder controls affect accuracy?
Again, the same thing, not only utilizing, as I said in the presentation, a high accuracy load cell, but you also want a very fast-acting controller. When you're dealing with the short-term time measurements like you are in the continuous processing requirements, as I said before, 5 seconds, second to second, you need to have a controller that is also taking measurements at a very fast pace. K-Tron's SFTs actually are capable of delivering that high resolution in 80 milliseconds. The loss and weight controllers actually weigh 112 weighments every second. And this is especially important when you're dealing with low rate feeding, as Suha was talking about before. The lower the rate and feed, the higher the deviations in accuracy. So you want to make sure that the controller that you use and the load cells that you use are designed for the higher resolutions, especially at those lower rates, as well as the fact that you're taking as many measurements as possible in order to get the proper mass flow from the feeder.
Okay, next question. Since the mixing process can be high intensity, are there any concerns with regards to temperature rise across these units?
This is a very good question. Obviously temperature rise is a critical issue, so we have run some tests on our module mix where, we picked a very dense material and ran the unit at its highest speed and measured the temperatures of the product coming out as well as the chamber itself. And we saw that typically we saw about a temperature rise of 1 degree to 1.5 degrees centigrade. This is primarily due to the fact that the material does not stay long enough in the chamber to pick up heat. So, short answer, there is really not much of a concern of temperature rise.
Okay, next question. You mentioned rates of 20 to 150 kilograms per hour range. What can be done for these applications that are of lower rates?
Sharon, I'm going to answer this one, but it also relates to, obviously, K-Tron's feeders as well. The issue is this is a generic range that we're providing. What happens is in the mix, typically the API is this small fraction ingredient in the 0.5% to 2% range. So when the total feed rate drops below these numbers, say, let's say 10 kilograms an hour, at a 0.5% fraction API, you're talking 50 grams an hour feed rate. So now the issue becomes, like Sharon repeatedly mentioned, as the feed rate drops, the accuracy becomes an issue. You need to make sure that you can get a feeder that could cope with the accuracy required. So it's not really the shortcoming of the mixing, but finding the proper feeding technology to make sure you can get an accurate feeding. Sure.
Yeah, one additional point too that's very important is at the lower rates of feeders, typically, and this pertains to lower than 100 grams per hour, for example, everything matters in regards to the accuracy and the performance of the feeder. Things like screw fill obviously are always an issue with the material, but even the issues that I talked about before, such as vibration that may be occurring in the plant. If you're working with a feeder that is close to a downdraft or in a downflow booth, for example, drafts and air currents will come across the scale because the scale, again, is designed for extremely low rate feeding. It will affect the feeder performance, so you want to make sure that the unit is isolated. K-Tron's low rate feeder, for example, goes as low as 20 grams per hour, but it's in its own enclosure or draft shield to prevent that. So it's very important that the lower rate you go, everything matters. So you have to take a look at the overall environment and the actual setup and how it relates to the mixer and connect it to it to make sure that you get the most accurate design.
Okay, next question. How do flexible wall design feeders affect feeding?
There are a number of different feeders out there, and flex walls are one of the types that are used to help to get the material into the screws. The problem with a lot of flex walls is they also promote packing with cohesive materials, and unfortunately in the pharmaceutical industry, a lot of the APIs are very cohesive, as well as many of the excipients, things like micronized lactose, for example. So the idea is you want to make sure you have consistent screw fill. You don't want to have the packing that occurs, or then you're going to have issues with material going into the screws. The other issue is the liner itself is difficult to clean, and the actual maintenance of the paddles can be difficult as well. So that's one of the reasons why Catron actually now has what's called an active flow, which I referred to a little bit in the presentation. It's actually an external device that's not part of in contact with the product. That is real time, so that the measurement or the signal from the loss and weight fader, when it requires or if there's an issue with the bridge, it will actually cause the vibrator to start, and then when the issue is back in line with the set point, it will cause the vibrator to stop. And so then that avoids the problems that you have with traditional, just regular vibrators that are put on hoppers and cause excessive packing.
Okay, next question. How much material will be left in the chamber once the process has been stopped?
Yeah, I think this is for me. As far as if we're talking about the mixer itself, the modular mix, as I mentioned before, at any given time has a very small amount of material because it's an annular mixer, which means there's a small gap around the housing that the material is in. And so with that, typically we're talking about less than 0.4 liters of material being in the hop or the chamber at any given time. So this makes this the residue very, very small at the end compared to the other technologies which use a bed of material. This is basically 5 to 10 times less, basically, your losses will be.
Okay, next question. What is the most common method for refill devices?
As shown in the picture that I showed you before, because of the way that the pneumatic receivers work and because the butterfly valves are generally fast-acting, that is usually the most often the device that you see. The other thing is that when you have a number of these feeders, like with multi-component mixes, sometimes we've had applications where it's 5 to 6 ingredients being mixed in a mixer. You don't have a lot of space above the feeder hopper to put in these refill devices. And pneumatic receivers or vacuum conveying devices are actually best suited for that. Finally, in the pharmaceutical industry, you also obviously always have to take a look at the overall cleanability of the system. Besides making sure that the feed system is reliable and also tight, like with the butterfly valve, we also want to make sure that the system can be designed to be taken apart and cleaned. The Catron systems that are utilized are actually completely designed to be clean in place with spray balls and or complete stainless steel construction so that the overall design itself can be taken apart easily and quickly.
Okay, we are starting to run short on time, so we're only going to take 2 more questions. What effect does screw fill have on accuracy?
Just like I was talking about before, screw fill is one of the most important things, and making sure that the material gets to the screws is going to affect the overall performance of the feeder. As I talked about before, making sure that the overall design of the hopper is done so that the feeder material or the material goes directly into the screws. There are different hopper or configurations on the actual bowl itself or the feeder device where the screws are that we can open that up. Catron actually has a new design that allows for better screw fill for more cohesive powders, because if the material does not get into the flights, then obviously it's not getting to the process, and as accurate as your feeder or your load cells are, that's not going to help you. So the best way to design it is to make sure that you have optimum design. The other thing is the type of screw that you use. If you have a very difficult problem with material and you have a very fine-pitched screw, sometimes the actual flights don't pick up the material and then it doesn't flow downstream. So you want to make sure that you have the proper screw flight configuration in order to take the material that's being delivered to it.
Okay, and our last question for today. You mentioned a 20 meter per second tip speed with our mixer. At these speeds, is there any chance of grinding of the product taking place?
You know what, this was certainly a concern for multiple customers that we tested with. So, we looked at the data and one of the things that is apparent in this setup is that if you have the bed of material in the unit, the typical RPMs are low, so you're not going to see a lot of size reduction taking place. On the other hand, with the modular mix, and if you're running the higher speeds, there is an actual air flow or air volume that's circulating on the outside chamber, and the feed material gets caught up in this chamber, so it's really not impacting with the paddles, but the material moving along with the air along the circumference. So even with weak, material, we have not seen any, particle size reduction.
Well, thank you very much, Sharon and Suha, for the presentation today. That concludes the question and answer portion of the presentation. We remind you, if your question was not answered during the presentation today, someone will be contacting you offline with a response. As a reminder, the presentation has been recorded and will be posted to the Hosokawa and Catron websites within about 48 hours. You will receive an email when they become available. Thank you very much.